Welcome back. This lecture is going to be about hydrocarbons. The goal is to draw structural formulas and name hydrocarbons. And really, we're not going to focus on naming hydrocarbons so much as we're going to focus on writing structures for the name. We want to recognize and draw structures of geometric isomers and optical isomers, and we want to be able to describe chemical and physical properties of hydrocarbons. So let's have a quick reminder of the different types of hydrocarbons. So hydrocarbons are compounds with carbon and hydrogen in them. And so alkanes are hydrocarbons. There's no carbon-carbon double bonds and no carbon-carbon triple bonds. There are alkenes where you have to have a carbon-carbon double bond. Alkyne, you have to have a carbon-carbon triple bond. And an aromatic, you want 6 carbons with what looks like 3 double bonds in the middle of the ring. And clearly, if these are 2 different functional groups, then these double bonds are not the same as these double bonds. And then there are cycloalkanes, where you have a ring of carbons. So let's look at the properties of these different types of hydrocarbons. Alkanes are considered to be saturated. So there are no multiple bonds in these compounds, and it really means that the carbons have the maximum number of hydrogens bonded to each of them. Alkenes are considered to be unsaturated because when you have a carbon-carbon double bond, if you got rid of the double bond, you'd have to add 2 hydrogens. So unsaturated means it does not have the maximum number of hydrogens. Alkynes are also unsaturated. Aromatics are unsaturated. Cycloalkanes, on the other hand, are saturated because there are no double bonds and no triple bonds. For reactivity, they all combust. Combust is the reaction with oxygen, which is really an oxidation reaction. And you form CO2 and H2O. Now, there's another type of reactivity, and it's the reactivity with halogens. Alkanes will react with halogens, but very slowly, and it requires light. Alkenes react with halogens very quickly, and it does not require light. Alkanes are like alkenes. They react with halogens very quickly and do not require light. Aromatics do react with halogens, but only with a catalyst. And finally, cycloalkanes are just like alkanes. They react with halogens, but very slowly. The state. The small alkanes, small molar masses, are gases at room temperature. Same with the alkenes and same with the alkynes. The smallest aromatic is actually a liquid at room temperature. It's called benzene. Cycloalkanes, the small ones are gas at room temperature, and then the larger ones start to be liquids, and eventually the really large ones are solids. Isomerism. Can you have cis-trans isomerism with alkanes? The answer is no. Can you have it with alkenes? The answer is yes. How about alkynes? No. How about aromatics? No. And cycloalkanes? Yes, you can have cis-trans isomers. So let's look at the isomer idea with hydrocarbons. Same molecular formula with different structure. Structural isomers, you have a different set of bonds. So here's an example of 2 structural isomers. In stereoisomers, they have the same set of bonds, but different spatial arrangement of atoms, and they're locked into those spatial arrangements. So here we have the cis-trans isomerism, which is called geometric, but also I like to call it cis-trans. You can see both hydrogens in this one are on the same side. Remember, the hydrogens are implied, and here the hydrogens are on opposite sides. So cis and trans. Here, the hydrogens are on the same side. They're pointing down. So this would be cis, and here the hydrogens, one is up and one is down. This is trans. And then there's optical isomers where the carbon has to have 4 different things attached to it. So if we take a look at this central carbon here, do you see that it has a CH3 attached to it? And it has a CH2, CH3 attached to it? And it has an OH attached to it? And the last thing it has attached to it is a hydrogen. None of those are the same. So here, that is a carbon, that is a carbon, but that doesn't mean they're the same. They have to be exactly the same. So this is a CH3, this is a CH2, CH3, they're not exactly the same. Here's another example of a optical isomer. This guy has 4 different things attached to it: a hydrogen, a chlorine, a fluorine, and a bromine. So let's look at what we call straight chain hydrocarbons. These are hydrocarbons where there's no branching. In other words, there are only carbon-carbon single bonds and carbon bonded to one other carbon, or carbons bonded to 2 other carbons, but you don't have any carbons bonded to 3 carbons, no branching. So here, these are the 10 hydrocarbons that are straight chain that you want to memorize. 1 carbon, 4 hydrogens, it's called methane. 2 carbons, 6 hydrogen, it's called ethane. 3 carbons and 8 hydrogens, it's called propane. 4 carbons and 10 hydrogens, butane. Let me write down those formulas for you. CH4, C2H6, C3H8, C4H10, C5H12. You'll notice that the number of hydrogens increases by 2, whereas the number of carbons only increased by 1. So here, I'll let you figure out what the formulas are for these, but you can see that in general, the formula is CnH2n plus 2. Okay, and then if you have 6 carbons, it's hexane. 7 carbons, it's heptane. 8 carbons, octane. 9 carbons, nonane. And 10 carbons is decane. So these are the straight chain hydrocarbons. Now, let's look at structural isomers of alkanes. So let's look at the formula C4 or CH4. Here, I want to do these as line drawings. There is no line drawing of CH4. Remember, a line represents a bond between 2 carbons or between a carbon and something else, right? So here, this is how you might try to represent CH4, simply with a dot. Now, that doesn't make any sense, because is this a period? Is it a dot on top of an I that got misplaced, or what? There is no line drawing for methane. This is ethane, and there's no line drawing for this also, because we could draw something like this, where there's a carbon at each end of that bond, and then you add hydrogens. But the problem is that looks like a hyphen, or a backslash, or a forward slash, or an L. So there is no line drawing for ethane. But for propane, there is a line drawing. It looks like this: 1, 2, 3 carbons plus add hydrogens, you get 8. Butane, 1, 2, 3, 4. Now, there are 2 formulas, or 2 isomers that are structural isomers that have this formula. If you take both of these and you draw in all of the hydrogens and all of the carbons, you'll find that they're both C4H10. And here there are, 3 isomers of C5H12. So I've drawn one of them. Notice that the first isomer you draw for each of these is the longest one that you can draw, where it's like a zigzag. So this is 5. And if you fill in the hydrogens, you'll get 12 hydrogens automatically. This one, you'll notice, instead of drawing 5 in a row, I drew 4 in a row, and I added 1 line to this somewhere. Now, I didn't add the line to the end, because that would be the same as this guy here, just, turned upside down, if you will. And I didn't add the line over here. I added it at one of the inside carbons. Now, it turns out that this is the only one that has 4 carbons in a row. What about 3 carbons in a row? Is there a isomer of this I can draw that has 5 carbons and 12 hydrogens? Well, if I put one of the carbons on the end here, I have 4 in a row, which is going to be looking just like that. And so this is not really an option, but I could do this. So how many carbons are here? 1, 2, 3, 4, 5. 5 carbons. How many hydrogens? Well, how many hydrogens on that middle carbon? None. How many on that one? 3. 3, 3, 3, which adds up to 12. So these are all the structural isomers of alkanes. And the method for getting these structural isomers is to do the following. So we're going to do the 5 structural isomers of C6H4. And I'm going to show you my method for doing this. So the first thing you do is you use the line drawings and you make the longest. So here I want 6 carbons, 1, 2, 3, 4. So 1, 2, 3, 4, that's 5 carbons, that's 6 carbons. Now, when I draw the line drawing, will I automatically have 14 hydrogens? And the answer is yes, as long as I don't have a ring here or a double bond or a triple bond, I'm going to be fine. And so here, if we fill this in, you can see I've got 6 carbons, 1, 2, 3, 4, 5, 6. And if I add hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14, I'm going to get the correct number of hydrogens. So when you're trying to draw the isomers, the first thing you do is you draw the longest one. And then you make the longest one, the longest chain of carbons, one shorter. So this has 5 carbons in a row. And I need to add another carbon to this. So where do I add it? I add it on that first hill. And these two are different from one another. You can tell that in this, I have a carbon that's bonded to 3 other carbons. And in here, I don't have any carbon that's bonded to 3 other carbons. So these are isomers. Turns out there's another one, and it's here. All right, so I have 1, 2, 3 isomers with the formula of C6H14 so far. And here, I'm going to leave it to you to fill in the hydrogens on these guys to make sure that you do indeed have 14. You should find that you do. If you don't, then you've made a mistake in filling in the hydrogens and carbons. Now, these two are different than one another. If we look at the names of these, this is called hexane because it's got 6 carbons in a row. This has 5 carbons in a row, so it's called pentane. Now, for these 5 carbons in a row, I'm going to redraw this. We number the carbons 1, 2, 3, 4, 5. And this right here is a 1 carbon unit, which is called a methyl. So a straight chain 1 carbon unit is called methane. What happens if it's a piece attached to a longer chain, something called a substituent? Well, then it's called methyl instead of methane. Now, we want to tell people that this is attached to carbon number 2. So this is 2-methyl pentane. Now, what is this guy going to be called? Well, it's also pentane because the longest chain is 1, 2, 3, 4, 5. But we have this 1 carbon unit attached to 3. So that's 3-methyl pentane. Now, when we take a look at this, we could put that other carbon on this 1, 2, 3, 4th carbon. And you might wonder, so what's the name of this guy? The name of this guy is 2-methyl pentane. Now, you'll notice that these two have the same name because these two are the same. All we've done is we've drawn it backwards, so to speak. Okay, so the idea here is that when you're naming these, you want to number the parent chain, that's the longest chain of carbons, and you want to start numbering at the end that is closest to the first branch. So this is all of the ones that we can draw that have 5 carbons in a row. So now we go with 4 carbons in a row. So what are the possibilities here? I could do that, and this would be called 2,2-dimethyl butane, because the longest carbon chain is 4 carbons long, so that's why it's called butane. This is a methyl and this is a methyl, so 2,2-dimethyl. You might say, well, why do I have to write 2,2-dimethyl? Why can't I just write 2-dimethyl? Well, because there's an isomer of this one, and it looks like this. So what would we call this guy? This would be called 2,3-dimethyl butane. Okay, so how many isomers do we have for this C6H14? We've got 1, 2, 3. This is a repeat. 4 and 5. Okay, so are there any others we can do? Well, what if I did this? Well, this would be 2,2-dimethyl butane. Okay, so that's not a new one. And let's see, what about 3 carbons? So here I have 3 in a row. Now I want to put the other 3 on this, and I could try something like this, right? 1, 2, 3, 4, 5, 6, and this looks like something different than everything else I've drawn here. However, 1, 2, 3, 3, 4, 5. The parent on this one is 5, so that's pentane. And this guy is a 2-methyl. So this guy is indeed that guy, and that guy, we've already drawn it. So the idea here is that when you are trying to name these, for naming, the first thing you do is find the longest chain of carbons. And that gives you the parent name. And then 2, you number end to end. And you start at the end closest to a branch. And then you identify the branches. And their location. So let's take a look at the possible branches. These branches are also called substituents. So if you have a CH3 as a branch, it's called a methyl. If you have a CH2CH3, it's called an ethyl. If you have a CH2CH2CH3, it's called a propyl. And if you have a CH and a CH3 and a CH3 like this, it's called an isopropyl. You can see that these 2 substituents look similar to one another. There's 3 carbons, but this branch is attached by an end carbon. This branch is attached by a middle carbon. There are some other substituents that you might want to know about. For instance, if you have this, a chlorine, it's called a chloro. If you have a fluorine, it's called a fluoro. If you have a bromine, it's called a bromo. And if you have an iodine, it's called iodo. Except for with this one, when you say it, you have to shrug your shoulders. Iodo. Okay, so these are some substituents that you probably want to know about. So you identify the branches and locations, and then you write the name with the branches first in alpha order, then the parent. And you want to make sure you add the location of the branch. So let's take a look at an example where we name something. I'm going to put a chlorine here and a chlorine here, and a chlorine here. Okay, So we can see that the longest chain is 1, 2, 3, 4, 5, 6, 6 carbons long. So the parent name is going to be hexane. Now, where do we want to start numbering this? Do we want to start numbering from the left to the right or from the right to the left? And the answer is we want to start here. 1, 2, 3, 4, 5, 6. The reason we want to start here is because we get a branch on carbon 1. If we start here, our first branch comes on carbon 3. So we want to start on the right so that we get the branch to be closest to the end, okay? So here, what is this guy called? It's called 1-chloro. What is this guy called? It's called 3-chloro. What's this guy called? It's called 4-chloro. So when we put it all together, we say 1, 3, 4, trichloro, hexane. And that's how you name it. Why do we say 1, 3, 4 trichloro? Because there's a molecule out there that's actually 1, 1, 2 trichloro. So we're trying to tell people where every one of these 3 chlorines are. Okay, so now you see how we name these guys. And now we're going to try to draw all the structural isomers of, oh, we already did this one. Sorry, that was the problem we just did. So hydrocarbons, drawing hydrocarbons from the name. Start with a parent, number n to n, and then add the substituents. So here's some of the substituents we've seen. Let's take a look at some examples. So this is something I will almost definitely put on the test for you, if not your quiz. And the reason I'll put this on your test is because you fill in the answer, and so you have to draw the answer. On the quiz, it's hard for me to do this. So let's draw these. So when you draw these, you start with the parent. This is heptane, which means we need 7 carbons. So 1, 2, 3, 4, 5, 6, 7. I have 7 carbons. Now I'm going to call this carbon 1, 2, 3, 4, 5, 6, 7, because when I'm drawing this thing, I get to choose which side I want to call number 1 and which side I want to call the end, if you will, number 7. And I like to go from left to right. It's very conventional. So here I have a 2-methyl. So here's carbon 1, here's carbon 2. That's going to be a methyl. A methyl is a 1-carbon unit, and you can see I've added 1 carbon to carbon number 2. Now, ethyl is a 2-carbon unit. So 1, 2, 3, 4, 5. Here is a 2-carbon unit. Now, could I have done this differently? Could I have taken this and drawn it that way? The answer is absolutely. Both of these are correct for this particular name. So that's A. Let's look at B. 2,2-dimethylbutane. So what are we going to draw for the parent? 4 carbons. So once you start drawing the zigzags, you count 1, 2, 3, 4. Go ahead and touch each carbon. Now, if this is carbon 1, this is carbon 2, I have to put a methyl on carbon 2. So there's a methyl. And I have to put another one on carbon 2. So there's 2,2-dimethylbutane. Okay, so let's look at C. So C, we have to do a 2,3-dimethylbutane. So here's my butane again. Here's carbon 2, and here's carbon 3, and I put a methyl on each of those. And lastly, well, not lastly, I have 2 more here. So let's look at this 1,2-diethyl cyclobutane. So for letter D, I've got to do a cyclobutane. So cyclobutane sounds like a circle of carbons where there's 4 of them. So that's what you're going to draw. Now, which one of these do you want to call carbon number 1? It's your choice. I'm going to go ahead and start over here at carbon number 1, 2, 3, 4. I like to go clockwise. So 1-ethyl. So here's an ethyl, 2-carbon unit, 2-ethyl, There you go. This is 1,2-diethyl cyclobutane. Now, E is supposed to be a fun one. Let's draw 1-cyclobutyl 2,3,4,5 tetrapropyl cyclopentane. Start with the parent, cyclopentane. Cyclopentane is going to be a house. Cyclobutyl, so this is going to be a 4-carbon unit. That's a circle attached to carbon number 1. So you see that's a 4-carbon unit attached to my cyclopentane. Now that's carbon 1, so this is 2, 3, 4, 5. And on carbon 2, I have a propyl. So here's my propyl. One, two, three. Carbon number 3, I have another propyl. So I'm going to do this. Let's see, I'm going to start this one over because I want to make this look kind of neat. So let's see, we're going to do this 3-carbon unit. And here I'm going to do this. And here I'm going to do that too, because number 4, there's a propyl. And then here, I'm going to do that, 1, 2, 3. So it's a dancing man. 1-cyclobutyl 2,3,4,5 tetrapropyl cyclopentane. All right. Now, if we, I don't know how to make this a Burning Man, but we'll leave it at that. So that's how you draw these guys. Now let's take a look at an example here where we want to name this. So here, I'm going to count the longest carbon chain. 1, 2, 3. I think I can do better. 1, 2, 3, 4, 5, 6, 7. Well, that looks okay. How about this one? 1, 2, 3, 4, 5, 6, 7. Well, no matter how I cut it, the longest carbon chain is going to be 7. So I'm going to stick with these here that are on the bottom. And what do you call a parent chain of 7? You call it heptane. Now, which end do we want to start numbering at, the left or the right? And the answer is whichever one is closest to the branching. If I start here, 1, 2, the branching starts at carbon 2. If I start here, 1, 2, 3, the branching starts at carbon 3. So I'm going to start over here so I can start branching at carbon 2. So what does that make this CH3? It makes it a 2-methyl. 1, 2, 3, 4, 5. So this one branches on carbon 5, and that's a 5-ethyl. So how do I put these 3 things together into a name? And the answer is alphabetically. Naturally, the parent name goes last, but the substituents are placed in order of alpha order. E comes before M, so ethyl comes before methyl. 5-ethyl, 2-methyl heptane. Okay, let's see now. So that's the end of this section. We'll see a homework problem associated with that. The next section is about reactions. So get ready to play the next video.